Hello guys, we on this video want to show how to use graphical approach to resolve a linear programming problem, you know, minimization case. As we mentioned in our previous video, for minimization case we have about 4 steps. So we're going to use the steps to resolve this particular problem. You can see the objective function, you see a set of structural constraints and non-negativity constraints. You know, you would have noticed that for our minimization case, we have majorly the uh, greater than or equal to the equality signs. So we'll quickly do that. Solution step one, which is inequalities to equalities, which is utility in standard form. We have 28 x1 minimize c to the raise s1 plus 30 x2 subject to x1 plus 2x2. Now assume that is equal to 40. Then 4x1 plus 2x2 will now be equal to 60. Of course, x1 here will be equal to 5. x2 here will be equal to 5 as well, where x1, x2 will be greater than or equal to 0. So, having standardized, the next will be to compute our coordinates. Second step will be to compute our coordinates. It's called computation of coordinates. Of course, computing the coordinates entails holding one decimal variable constant, which of course translates to holding it to 0 and determining the value of the other one. So for this, we have 1 or I, we have that x1 plus 2x2 is equal to 40. So if we hold x2 constant, x1 plus 2 by 0 is equal to 40, such that x1 will be equal to 40. Then if you hold the other x1 to constant, we have that x1 plus, we have that 0 plus 2x2 will be equal to 40, such that I have 2x2 will equal to 40, so that x2 equal to 40 by 2, which is 20. So we can use this place. I can clean this now. So quickly clean this and use this place to put my coordinates. Which is my x1, x2, For the first one, we have when x1 is 40, x2 is 20. We have 40, 20. I'll compute the rest here. We have the second one here, which is 4x1 plus 2x2 equal to 60. It is, if I hold for x2, I have that 4x1 plus 2 by 0 is equal to 60. So 4x1 is equal to 60 and x1 is equal to 60 by 4, which is 15. Then if I hold for x1, I have that 4 by 0 plus 2x2 equal to 60. So 2x2 will be equal to 60. So x2 will be equal to 60 by 2, which is 3. So for number 2, when x1 is 15, x2 is 30. Then for structural equation 3, it's a minimum requirement, or maximum requirement rather. So I have x1, I have x1 to be 5. So this is 3 here. x1 will be 5 and 0 or 4. x2 will also be 5, will still be 0 and 5. So having done this, we will use this to graph the constraints quickly. Step 3 now. Step 3, which is graphing the constraints. Now these are in 5, so and the maximum is 40. So let me have one cm to represent 5 units. This is my 0 point. This is of course my x1, which is my x2. So that's y. This is also my x. So I have has been mentioned in a previous video, and of course when you use your graph you have more accuracy. So I have 5, 10, 15, 20, 25, 30, 35 and 40. Then we have 5, 10, 20, 25, 30, 35, 40, 45, 50. That's the case. Okay. So now we have our graph where 1 cm will be representing 5 units. So now this is the first um, constraint. So we have that when x1 is 40, x2 is 20. So when x1 is 40, x2 is 20. This is my x1. My x1 is 40 here, and my x2 is 20. So we're going to join the 2 points. 40 for x1, 20 for x2. Don't mind our drawing. When we use your graph sheet, we're going to record more accuracy. Of course, what we do in graphing the constraints is we are looking out for the best combination, the optimal combination, of the production of the decision variables. So, which is a point called a feasible region. So, your guide to identifying the feasible region is the equality or inequality sign. So for this first constraint is of the greater than or equal to sign. So which means that anything, all the values beneath the line are not desirable. So we'll be going for the point above the line. So for this, we'll be shading off this. Alright, for the second structural constraint, when x1 is 15, x2 is 30. So x1 is 15. Oh, we jumped 15. So 15 is somewhere here. X1 is 15. Then x2 is 30. So this is 30. So we're going to link up 30 with 15. Which is this. And it is also of greater than or equal to type, which means anything below the line, we do not want it. It is the values above the line that we are searching for. So we are going to shade off these parts. Now the maximum requirement. For x1 we have 5. For x2 we have 5. So for x1, which is here, we have 5. And we're going to do a perpendicular line by 5, which is sorry. So this is for production requirement for x1, and for x2, which is also 5, we're going to also do a perpendicular line to x2 5. So we also get this. And do not also forget that it is also of greater than or equal to type. So anything beneath is not desirable. Just like this, anything beneath is not desirable. So this is our feasible region. Alright, so having done this, having graphed our constraints, the next step will be to test the extreme corner point. And we've mentioned it earlier in our previous video that this feasible region is a combination area. It's a production combination area. This is where the optimal production plan, optimal production combination will come out from. So any point within the feasible region will give you a combination. But it has been proven that the optimal combination plan will come from the extreme corner points. So for this particular case, we have one, two, and three extreme corner points. So we will be testing the extreme corner points only. So we'll label this A. The second one will label it B. And the third one will label it C. So we'll be reading off this value, determine the values, and substitute them in the objective function. Of course, we are minimizing, and any one that gives us the minimal combination in terms of cost will be selected. So we are going to impute them here when we read off. So now at point A, sorry, we have x1, x2. At point A, I have that x1 is 5 and x2 is, since it's this point, I have that x2 is about 21. Then at point B, which is this point, I have that x1 is about 6.56. So point B, x1 is just 6. We keep emphasizing that if you use your graph sheet, the reading will be more accurate. Then on at point B, you have about 16. Then at point 6, you have that x1, okay, we're going to take 30 for x1. Then of course for x2 it is 5. So we're going to substitute values into the objective function to determine the best combination as it relates to cost. So the objective function remains to maximize cost, or rather to minimize cost which is 28x plus x1 plus 30x2. So now the next point will be substituting. I clean this. Next point will be point 4, testing the corner points, extreme corner points. So now At point A, we have 28 by 5 plus 30 by 21. The next will be for at point B, we have B, we have 28 by 6 plus 30 by 16. What do we have? Then at point C, we have 28 by 30 plus 30 by 5. Having computed them now, the values now, the optimal combination will be the least, which the combination that gives us the least cost, which is a combination B. So the combination will be to produce 6 units of x1 and of course 16 units of x2, because it's going to give us the optimal cost, the minimal optimal cost of 648 naira. We hope that you find this video relevant to your career. Thank you very much.